Okay. So the theme of my lecture today is the least squares problem and engineering. So the reason I picked this problem is we do least squares. We do least squares right from 8th or 9th grade. We do it in physics first, chemistry, we do least squares. But we don't appreciate that least squares is so impactful. It goes much beyond the curve fitting that we did in our physics and chemistry labs. So that's the theme of this. So least squares goes on to Kalman filtering, it goes on to training neural networks. So it's with us today. There are many algorithms based on least squares which operate on your cell phone and other devices. Okay? So I request you to once again make this interactive. There were just a few people who were asking questions last time. Let's make it more. So let's try. Okay, so this is broadly how my talk is sort of structured. So curve fitting in the school laboratory, the vector space picture, Fourier series. I think many of us have heard of the Fourier series. The Fourier series also comes about as a result of least squares. Okay? The Kalman filter, the least squares in modern AI applications. Okay. So let's say we look at a simple problem like the extension of a spring with a load. So this is the load and the extension, and we are aware that from the physics of the spring that there is something called a Hooke's law, which means that displacement is proportional to x. So what is it that we are looking for? We are looking at finding out what that k is, right? What's the constitutive relationship between a given x and the force, right? So you get a set of data points. So now you need to find k. You can look at those data points and say, okay, this is approximately k, but that's not a scientific way of doing things, right? So what do we do? Right? We construct, I hope my cursor is visible, yeah. We construct a residual. What's a residual? If, okay, I started with just k, here I'm moving on to mx plus c, so I'm giving an equation of this form. So for an xi, the value that I expect of y is mxi plus c, assuming I don't know m and c, right? And then I see what is the difference between that and what is yi. I have a set of data points, right? And then I sum up the square of these errors. Straightforward, right? I just sum up the square of these errors, right? And then I find out that m and c which minimizes this cost. So if that were the case, how would you do the problem? So we have a problem, we need to find m and c. It's over a set of data points. Okay, n, let's say n was 10. How would I find m and c? How would you do it? Can somebody give me yourself? Yeah? You can sit down, yeah. Just be a bit louder if you don't mind.
Sir, we can differentiate the residual and try to find out the position where S is minimum.
You will find out the position where
It's like M and C for which S is minimum.
What is that? How will you find that out? What do you do? There's one crucial point you missed.
So differentiation.
Differentiation
and minimizing, like ds by dm and ds by dc is 0.
Anybody else can complete this? Anybody else who can complete? He says take the derivative. That's right. But then do what? Yes? Right. The slope of that should become 0, right? What is the value of m and c where the slope becomes 0, right? And that's the point where you are minimizing the error, right? So that's a calculus way of doing things, but that's fine. That's finding out the slope and finding out m and c, that's all fine. But then there is a larger picture, so which is what we want to get. So let me attribute these notions to people who actually who discovered these, Gauss and Legendre, and as has been pointed out by you, so you can look at the slide, I won't go. So this is pure calculus. So far, pure calculus. We've set up a least squares criterion. We've taken the derivatives, we've set them to 0 to find out what m and c are, right? But the larger picture is far more beautiful than just this calculus. Okay. So I have a couple of pictures, but in my talk today, I don't have any videos. Today's talk is devoid of videos. I couldn't find anything which was sort of educative and thrilling. Okay. So this is just some factual information about Gauss that I picked up from one of the sites. And now let's write this problem in a slightly different way, right? So I have a vector, so these are n real variables, right? N real variables, and I have an approximation symbol here, and I want to find these xi's so that this column vector is as close as possible to this. So rather, I'm given the xi's, I want to find m and c so that this resultant, because this resultant is also going to be an n column vector, right? And a column vector with n elements, I mean, is as close to this. So then I have a slightly different problem. So I'm calling this now A and saying Ax hat. So this is the x hat is as close to B. So I've introduced a new notation, which is these parallel lines here with this 2 on top. So I'm sure most of you have seen it. So that's the square of the Euclidean norm, right? So that's the square of the Euclidean norm. So what is the geometric interpretation of this? I want to find that x hat so that A times x hat is as close to B as possible. And since it's a column vector, when I say proximity, I need to get some scalar into the picture. That's the norm, right? I need to get something which indicates the size of the proximity, which is what is in this case the Euclidean norm. All right. Now, when we began, I said we formulated a very simple least squares problem. We differentiated and found some 2 constants in the case of mx plus c. But then I said there's a larger picture. Then I brought in Ax hat and B and those equations, and I showed you the norm, right? So now this is where we jump into something which is more involved. The notion of proximity is not just between 2 column vectors or not between just those scalars I said. Proximity can also be in terms of functions. You give me a periodic function. So let's say I have this axis which is got functions from 0 to 2 pi. So it's periodic, so this repeats itself after this. Now, if I were given some other function, let's call this, so this is g and this is, I'll call this h, right? So now the question is, can I talk of something as how close is g to h? Have you ever seen this before? How close is g to h? In any course of yours, have you seen about, just as if I took the real line, let's say this is the real line, start, so this goes 0 and this way it goes to negative infinity, this way plus infinity. It's very easy for me, given 2 points, I'm more than happy to talk of their distance. But this seems slightly strange. So how many of you have ever come across proximity of functions in some sense? Nobody. Okay. All right. So now we have to set up something to talk of proximity of functions. Why is that? Why am I motivating this? Suppose you have a periodic function and you choose a set of periodic functions. Let's say you choose functions. So let me take an example of periodic function here. Takes these. I want to approximate this function by a combination of these. If you see that these problems now, I'll explain, they all start looking similar. What we started earlier to now, they'll all have a common theme. So let's explore that. And to do that, so why did I digress into all this? I need a notion called a vector space. Because all that we study as row vectors, column vectors, maybe real or complex, form a vector space, but unfortunately, the notion of a vector in our heads is always a directed line segment. So the minute you talk of a vector, the first idea you have is an arrow. Am I correct on that? Does everybody agree? Am I correct? Nobody thinks, if I told you this is a vector, you definitely not accept that, right? You say, that doesn't look like a vector, right? It is. In fact, this is just one small subset of what we call vectors, and therefore we need something called a vector space. So here are some examples. Polynomials. So what's up? So let me take, let's take a polynomial in the indeterminate t. When you describe a polynomial, it is an indeterminate, either t or x or y. So let me take a polynomial of degree n. It will look like this. Right? This is a polynomial of degree n, and often with students, they'd always want to substitute t for something. No, the polynomial is just an entity as it stands here with the t. You are not substituting for t and getting a number. This, just like this is a vector in its right, this is a member of a vector space in its own right. Okay, so what is this large family that we have? We said we could have polynomials, we could have functions, we could have random variables, etc., and we started with elementary notions. The thing is, what unifies all of these is that the underlying elements, like for example in the case of polynomials, they have something called a binary operation, that is, you can add two of them, and this operation has certain properties, right? For example, I can add this to another n degree polynomial. Do you agree? And you'll sort of by default say, yes, I'll add the coefficients. So if let's make things simple, let's take a second degree polynomial. And let's say we add it to something else. So the way you do this is a2 plus b2t squared, a1 plus b1t plus a0 plus b, right? And that's the way you do it. Now, in addition to that, there are some other features also. There are what are called scalars associated, which are called fields, and I won't get too much into the mathematical structure of these. And with all these operations and certain axioms that these operations have to satisfy, these polynomials, functions, random variables satisfy the same properties as what you had seen in vectors. So just keep that in mind. So now we have unified a whole set of objects using basic structures. So let me write down. So let's call this a vector space. So let's call these polynomials, in this case degree 2, the vector space. So there's a binary operation. Then there is, in this case, what is called a set of real numbers which associate with these vectors here. Which associate with these vectors. A simple example is if C is a scalar and I took C a2 squared a1t plus a0, then I would write that this is a new polynomial of this form. Okay. So there is an association of this scalar with this polynomial together. So let's not worry beyond that. But now comes something important. So does everybody have an introductory idea of what I am trying to say? That the set of polynomials, yes, questions? Okay. The set of polynomials, the set of functions over some interval, then a set of matrices, all these would have a structure very similar to what you studied in physics as vectors. What did you study in physics as vectors? Forces, velocities, accelerations, all vectors in R3. R3 was a vector space there. Okay, so let's proceed. Okay, so I'm now going to move to something which is geometric. So when in that column vector I described first, to talk of length, we used a norm. We used a Euclidean norm. So you just said x1 through xn, it was x1 squared plus x2 squared to xn squared, took a square root, right? Now, we want to talk of one more object. Why do we need that object? So here's a vector. I'm drawing a vector in the sense you learnt it the first time. Here's a vector. We have now associated a notion of length, and that notion of length was a norm. Okay? Now I want to do one more thing. I want to associate a notion of an angle between them. So this is one vector v1, v2. I want to associate a notion of angle. And why do I want to do that? Because I want to talk of perpendicularity between vectors. It's easy to see when I hold these two markers and say these are perpendicular, everything's fine, because that's the way we learn perpendicularity, right? But again, if I ask you, this is sine omega t and this is sine 2 omega t, is sine 2 omega t in this interval perpendicular to sine omega t? You're not sure. How can I talk of perpendicularity? So that's what we'll explore. So this notion with the angle we shall call an inner product, okay? All right. So now here are two, on Rn I have defined an inner product. Where did you encounter an inner product first time? I said you encountered the least squares problem in physics. Where did you encounter the inner product for the first time? Yes, who said that? Yes. And dot product was, what did it do? Right, in physics, could you give me an example where the dot product is used? Force into velocity, for F dot V or something like that? Yeah, perfect. So you see that in physics where you have two vectors, they get together, the dot product gives you a scalar, right? And so now we are going to extend that notion to something. If you look at this, I was talking of functions. Now I am defining what is called an inner product on functions. So before that, let's go through this side. So we need an inner product. It needs to have certain properties. These are the three properties the inner product should satisfy, which you can see that in what you are already familiar with, it satisfies these properties. But you can go back and check. If I took periodic functions, let's say this was minus pi and this was pi, so or 0 to 2 pi, and I took two functions, this would be a valid inner product in the sense it would satisfy all these properties. Okay. So now is where we are getting into the larger picture of things. We have just defined an object called a vector space and have said that there are two important properties we would like to impart to this object, that is the norm and an inner product, right? Now we'll see what happens. So what's given in this picture, I call this the projection theorem. So let's go from elementary notions to the projection theorem. So let me say I am in this plane of the board, and so this is your 0, and I have a vector like this, right? So let me call this a vector, let's call this A1, right? Now I tell you, give me that vector along, so let's call this in terms of what you are familiar with, x-axis, y-axis. So I tell you, give me the best approximation to A1 along the x-axis, a vector along the x-axis. So I'm talking some vector like this. I'm drawing it curly, but I mean like this. What will that vector be and how will you formulate this problem? I'll just repeat myself. I have a vector A1 on the plane of the board, which is given here. I want to find its best approximation in the x-axis. How would I set up the problem? Suppose this was the best, this was an approximation, A1 approximation. So let's maybe use a notation we'll come to later, call it A1 hat, right? If I give you this and somebody else tells you, no, it's not this vector, it is this vector. What is the criterion you need to set up to distinguish between which is the best vector? That's the optimal vector. You'll have to set up a notion of an error, right, between what exists and what is that. So how will you do that? So if I spoke of, so let's remove the green one. Yeah? And let's have this. So I'll talk of this as an error. Okay, why is that? Or rather, I'll do it the other way. I'll explain to you why. So if I talk of this as the error, then I have A1 hat plus E equals A1. Everybody see that? Now tell me, how will I find out what is the best A1 hat? Yeah, please do come forward, because this is very simple. I'm not even talking of something more abstract. Yes. Yourself, yeah. Sit down.
Be like closest to the X line.
Okay, it should be closest, but when you say closest, you have to give some way of measuring proximity, right?
It should be perpendicular with X.
What made you think it should be perpendicular to X?
Because if it is perpendicular to the like X, the perpendicular line would be closest to the point.
Okay, so perfect. What he's saying is, we've got E as this, and what's our objective? We'll use norms again. We want to minimize the norm of it, right? Or in other words, we wish to minimize that. Okay, I have to be a little bit careful. These are vectors here. I have to minimize. So I'll just put in a square here. I'm saying the square of the length. I want to minimize this A1 hat belonging to the x-axis, right? So how do vectors in the x-axis look like? They look like some alpha and 0 in the way you've done up, right? They look like that. Okay. And then he says the best approximation will be when this error gets perpendicular. What's the intuition? Why should the error be perpendicular? He's right. Yes.
That line is perpendicular to the vector.
Yes. Perfect. And another way of looking at it is this. See, if the error was not perpendicular, let's say it was this way. What does that mean? There is a component of the error which is here. You did not do the best possible job. You still had a component which was lying on the x-axis. But the minute it became perpendicular, you did the best that you could, right? So here is the, so there is the first thing or the theme of this lecture. It's a projection. So you are projecting this vector like this. The error is orthogonal. So the projection theorem, given a vector B, so I think I've used different, so maybe I'll rewrite these with that, or look at the picture there. Given a vector B and a closed subspace W. Okay, that's a little bit of jargon. Closed subspace. Let's not worry about that, but let's think of it in terms of a picture. Let's think of a plane. Say in this room, I have a plane, or think of this floor, right? I have a vector which is B. I want to find the best approximation of B on this floor, right? And I construct an approximation which is B hat, and then construct the error. And I can minimize the error, the norm of the error, when this is orthogonal to the plane. So that's the projection result. Do you see the intuition behind it? So we have to relate this to how we did our least squares. We still are nowhere near least squares. We are talking of an approximation in a subspace. So let's move ahead. So here is an important statement which you'll be surprised. Those who do Kalman filtering, many of you have done Kalman filtering. Kalman filtering works on this principle, that at every stage the error is orthogonal to the subspace, but in the case of a Kalman filter, that subspace is spanned by measurements because you're using measurements, right? Okay, so this is a takeaway from this slide. Okay, just to complete certain discussions, you can always think of vector spaces. So you have, I spoke of a subspace, right? You can always think of, if this were the plane of the floor, you could always have this subspace and a subspace pointing upward like like just a column vector here, and together that and this floor will give you any point in this room, right? So this is what this is saying. So it's not going beyond that. It's just saying that you have two subspaces, you have this and this. So this is in the context of the approximation, but you can call that a direct sum. So this is a vector space terminology. Okay, some more. Let's go back to remember I set up a problem here. Try to recall this problem. Now if you have solved this problem using just some sort of a mathematical argument other than this, what does the orthogonality principle say? It says that the columns of A, so what are we trying to do? We are trying to find that combination of the columns of A which is closest to B, right? So now this quantity here is the error. Now if we want to extend the notion of orthogonality, this error should be perpendicular to the columns of A. So this was A. So these were the columns of A. I think I took it as an, I don't remember what was the dimension I took it, right? So let's say it was M columns, and you were trying to approximate B with the best possible combination of these. If you approximated it with the best possible combination, so that's AX hat, the error in B should be perpendicular to the columns. Otherwise you could have done better, just as in the case of the orthogonality of the error in the simple R2 case. If this was not true, that is the columns of A were not perpendicular to the error, then you don't have the best possible estimate. Okay, and so that you can reduce this to this, so you have X hat equals A transpose. Okay. So just a summary of things. Okay. Now let's do this for functions. We did vectors in Rn. We started with the least squares problem. These are functions. So the procedure is the same. You do exactly the same way. You go about, the only difference is this key construction, and this key construction is what defines the orthogonality. Because now if you are talking of a best approximate, you need to show that that best approximation is perpendicular to the subspace. In this case, it's a subspace of all the functions that you have. So here it is. So this is an orthogonal basis. Okay, I think that's a word you probably have not heard of. Basis, is that heard of? How many people have heard of the word basis? Okay, a few of you, right. So that's like a basic construction for a vector space which has two properties. It's a set of vectors using which you can express any vector in the vector space, and they are all what are called linearly independent vectors. So it has two properties if you call a set a basis of a vector space. Okay, so these slides just indicate how doing the same, going through the same procedure, but now constructing this on functions, how can you get a best approximation to a function, a periodic function. And again the same, so the error. Remember this, we constructed as a set of vectors Sn, and now we are the subspace Sn, and given any other function we want to approximate this function with the best fit from Sn. So Sn is in the subspace spanned by these vectors, and remember now each of those vectors is a function. Each of those vectors is a function, and from our earlier notion of a vector as a directed line segment, we've come to accepting that vectors can be functions. Okay, any questions so far? So do you see the transition from vectors in the sense of vectors in Rn, the column vectors we saw, to functions and sets of functions, a basis in a function space, and an approximation to a function. Okay. So we saw this picture last time as well. So that was the Kalman filter, right? And Kalman's algorithm. So this is a sort of a repeat of the last lecture slide. Now, how do we talk of projections here? So I'm sort of covering this just to make it a little bit comprehensive. So in this case, when you implement a Kalman filter, most of you who have done it have looked at covariance matrices. You've looked at a mean of a Gaussian random variable. So things are a little bit different now. You went from vectors to functions, and now you come to random variables. So you have to define appropriate mathematical constructs. So one such is the expectation operator. So x and y being random variables, you can now define something like an inner product using the expectation operator. So from here, you can now talk of the Kalman, I hope my cursor is okay. The Kalman estimate, suppose this green thing was the span of the measurements, all the measurements that you had, then you are trying to approximate your true state, that's the red vector, with the best possible combination of your measurements, and that's what you're doing, right? And the Kalman algorithm works in a way that the error vector is perpendicular to this subspace. So here if you see below, this estimate that the Kalman filter builds, which is like a conditional expectation, that means my guess of x is based on my set of measurements, right? And this is such that the error is orthogonal to this subspace. So you see the power of orthogonality from a very elementary problem in curve fitting to Fourier series to the Kalman filter. It's all the same principle. So this is essentially the same. So all these, but now everything is in terms of an expectation. So that's what you need to. Okay, the last part. Everybody loves machine learning. Everybody loves ANNs, deep learning. These are the topics of today. So have you ever wondered when you trained a neural network, what were you doing? How many of you have worked on neural networks for some application? Yes. So maybe we'll ask you, how did you train your neural network?
We used a reinforcement learning for a line follow, which is part of eYantra.
Can you be a little bit more specific? I understand, I mean, you're saying reinforcement learning. So how did you change the weights, or, I mean, what did you do?
Yeah, so how we had it was we had like basically states and like rewards. So when it does a desired outcome, we basically reward the neural network. And
But how do you reward it? Is it a function? Is it some sort of a function which is a reward?
yeah, it's like a error function basically we used.
Okay, and suppose that error was large or small, what was the next action that you did?
If the error was like too large and like if it went off the line, we basically like reduced the rewards, and when it followed the line more precisely with less error, we gave it more reward.
Okay, all right. Does anybody else want to attempt what you did in neural networks? I'll be happy to have another answer. Training neural networks. Anybody else? Oh, there's a person behind.
So like,
Can you switch it on, please?
yeah, can you hear me, sir?
Yeah.
Yeah, I mean, first I just did simple linear regression. So linear regression, like, which is just one layer of.
Just so that everybody is on board. So what would you mean by linear regression? Just can I write it down?
Yeah, that's basically only one layer, or I'd say two weights that I tune.
Two inputs.
So I have multiple data points.
Okay.
It's the least squares method,
Okay.
but optimizing for two parameters. So I have two weights that are updated. So
So what would it look like? Would it be like weight 1 into some?
So yeah, W1 x1 plus W2 x2
Okay.
plus B, or
Okay, that's some bias. Okay, and then you would compare this to some given
so
output.
I have the desired output,
Okay.
and I have the input that I'm giving.
Okay.
So I would try to minimize the input with the
So you would try to minimize the
error between the square of the error.
the square of the error. And how did you do the minimization?
Yeah. So
How did you change the weights?
yeah. So like if so it depends on the error function. Initially, I just did linear regression. So I mean like mean square error. So you would do dou f by dou x. So basically partial derivative with respect to each of the weights, and those will give you more functions. So then you can write y2, which is the second step optimization, is y1 minus the slope times your training parameter. So your training parameter would be how fast you want it to converge.
Sure. So what he's talking about is he has an error function, he computes certain gradients, and then he changes the weights by moving along a certain direction of the gradient, right? So what he described is what is sort of written here. There's a difference here. See, now this function which I introduce here, which is a function of the xi's and the weights, is no longer everything that we saw so far had a nice linear structure. You talked of ax hat, and even the functions came from an underlying linear structure. But now for the first time you'll see something which is different. You may have things like sigmoidals and other things buried there. And now this is your loss function, which is what he spoke about. And how do you go about changing the weights so that you have a good performance of your neural network? So if you see that figure there, you update the weights, you go from your last weight and then move along what he described as the slope and come down with some step size eta. So is this similar to that? Okay. And yeah. So I think we are, maybe I have a few minutes more, but there's a summary of curve fitting, to inner product spaces, to Fourier series, to Kalman filters, to neural networks. So they all work on least squares and the projection. So the summary of this talk is from 8th grade spring experiments to spacecraft navigation and modern AI tools. You have one geometric idea. That's the least squares, and you have projections and things like that. So if you go through my slides, you'd get some of you could familiarize yourself with more of the structures. But as I said, the intent of this talk was, we are often buried with details of computation. We don't appreciate the larger picture. So, and the larger picture is everything comes down from least squares, everything comes down from a projection. So with that, I stop. I'll be happy to answer questions.